Intake systems, you love them or you hate them, or you're indifferent, which I suppose is fine too. We're going to look at two different engines that are approaching the same challenge, but in slightly different ways. We have the 0300 and our IGSO 480. So we'll start over with the IGSO 480. Remember, we have four primary components to any intake system. We have our air inlet up here, which this one is designed pretty nicely. The shape of this actually allows us to take advantage of ram air when the aircraft is in flight to produce higher intake manifold pressures, which is kind of nice. It's a little bit like boosting without anything that needs to boost. This is supercharged, so it's probably irrelevant anyway, but it's a nicely designed air inlet. And you'll notice as we come down our inlet further back through the trunk here, we're going to come to this bend right here, which goes up to our throttle plate. That throttle plate is going to be the entrance point, technically speaking, to where our intake manifold is. Now, we have a couple different things. We have our air inlet, but we're missing a fuel metering device, and we're also missing an air filter. Well, we know where our intake manifold is, so where are the other two? Well, there's kind of a difference about how they build this engine. So first of all, let's look at fuel distribution or fuel metering device. In this case, we have single point injection through a single injector, which goes into our supercharger section before this gets sent out to our intake manifold, and we have these familiar little 90-degree turn inlet pipes that go to the cylinders. So our fuel metering device is made up of a combination of this injection point along with our fuel injector on the other side that works in conjunction with our throttle plate. Now the filter, this one's kind of tricky. Our filter is actually located right here on the bottom of the engine. And you may be thinking to yourself, well, that's weird. We already have a path going into the engine, so why in the world did they strap an air filter onto the bottom of this trunk? Well, I'll tell you why. Reason being is this does not normally provide filtered air while the aircraft is in flight. Presumably, the reason they've determined that is, well, the aircraft is flying through the air, so there's probably not a lot of dirt and debris and squirrels and other small animals that can get sucked into it when it's at 12,000 feet, so we don't need to worry about it. So instead, what they've done is they come up with alternate filtered air. All that does is we have a control arm, which is linked up in the cockpit, so when the aircraft is taking off or landing, the pilot has the ability to switch to alternate air, which closes off the duct that's allowing ram air to come in, and instead draws filtered air through the bottom of the trunk and takes through the rest of the system. That's one way of approaching it. Other nice thing about this is you don't have to really worry about filter ice while you're in flight because, well, there's no filter for what's normally being used in flight. Now on the flip side, as we go take a look at the 0300, this is a little bit more simplistic, but maybe in some cases hard to see. So we'll dive in and take a look. First thing to notice right here, we have our air filter right up front. This is a non-serviceable element. A lot of people remember these elements that could be serviced. You'd wash them out, then you'd re-oil them with a special kind of oil. That's not what we're dealing with here. It's not your car's K&N filter. These are designed to be replaced each time. Now, on the other hand, we have our carburetor box, which does a couple different jobs. Half of that job is related to carburetor ice, which we'll talk about in a minute here. But we have our carburetor right here, which is our fuel metering device. And you'll notice it's bolted right to the bottom of the oil sump. That can be a little bit confusing because you think, well, where's the intake manifold and why is this going into the oil sump? Well, the reason for that being is we actually have piping that runs internally, or ducting that runs internally as a part of our intake manifold. So we have our intake manifolds here, which connect to the cylinders. It comes up through a pipe, and it actually allows the warm oil to preheat the charge a little bit. Now, you may be thinking, oh, I thought you were just telling me how great it is to have cold, dense air. Well, that's true. Cold, dense air is still the best thing. However, if it is too cold, then it actually makes it very, very difficult for the fuel coming out of this carburetor to emulsify in the airstream. So as a result, some manufacturers, you'll see this on older airplanes most of the time, will actually run part of the intake system through the oil sump to get some of that extra heat and to help the fuel and air to mix together so we have a nice, easy-to-use charge to promote burning. And as we get up to our cylinders themselves, you can see that our intake manifold here connects to the cylinder by means of one of these wonderful little intake hoses. these will be the bane of your existence, mostly because of intake leaks. They can be notoriously difficult to get to seat properly to make sure that it's actually bit on the wrong place, and they will cause leaks in your inlet all the time. They can be kind of tough to troubleshoot and figure out, so just keep that one in mind. Now back to the point about carburetor ice. Now we know that carburetor ice, we have a couple different forms. We can get impact ice that forms on the filter or filter ice, and then we get carburetor ice, which can form in the venturi of the carburetor. Basically, we have cold, moist air that's being taken in through the filter, gets up into a venturi, which drops the temperature further, and we introduce more liquid by means of fuel, which can cause us to start collecting ice. That is usually determined by a loss of performance on the engine itself. So what we have is this little muff that goes around the muffler, and what that does is it draws in fresh air. It's forced around the muffler, and there's all these little fingers sticking out that allow for extra contact area to transfer heat from the muffler inside this muffler jacket or muff that allows the warm air to get warmed up, and it exits through this bit of scat tubing and takes it out to our carburetor box. The way that this works is we have a lever that's up in the cockpit that as that's pulled, it goes switch, which is probably a little bit anticlimactic from this side. You can see our lever right here. This will move back and forth. When it moves back, it takes a door, and it's normally horizontal, and it will block off our filter entrance right here, which forces it to draw air from this fresh air inlet out through here and forces warm air up through the carburetor, which melts the ice. It is not designed to be run for long periods of time because long periods of operation can tend to cause overheating of our fuel air charge and potentially things like detonation and other unhappiness, but it will melt the ice over short bursts. And usually you can tell that you did have carburetor ice by the fact that you'll notice an improvement in performance once you return the carb heat lever back to its normal position. Here's a couple of endnotes to supplement the video. So Tempest is probably as good of a place to start as any when we talk about intake systems. Part that's interesting about this is ultimately their idea of an air filter. So you can see right here this large open cowl where we have an oil filter or oil cooler and a radiator, but through the center is the intake to the engine, which offered some preheating to help with carburetor ice and that kind of thing. But you see up here, this was a aerodynamic filter. I just point this out because it's kind of cool. You don't really see too many of these. The aerodynamic filter was effectively supposed to use airflow, since it had the oil cooler surrounding it, to prevent any foreign material from entering into the intake system, which is kind of cool as an aside, but it takes us into our conversation about filters. A couple things to note when we talk about filters. There's three primary types that we're going to look at. What you see right here is a paper filter. Now, of the three types, two are technically speaking serviceable, one is not. With paper filters like this, it's going to be very similar to what you see in any automotive application. You have a mesh liner on the inside right here, which is going to prevent these pleats from trying to crush or implode as they load up with material. It's pleated just like you'd see on an oil filter element to provide more surface area. And then this grating that you see on the outside is actually protection for the filter itself, and it also acts as an ice guard. And effectively all that's going to do is cause ice to accumulate on those grated pieces before it accumulates on the filter itself, which is something we can see from impact ice. You'll see different variations of that on different filters, but ultimately, as we talk about the three main types, you're going to have the flock or cellulose. Flock or cellulose is going to be serviceable, and it's serviced by flushing it with solvent, and then it's recoated with engine oil. Now, you don't see these very often anymore, realistically. They're pretty few and far between. One of the more common that you're going to see are paper filters. And when I say paper, it doesn't mean that it's legitimately paper. They actually have some new fiberglass constructions and things like that. But it's going to depend from manufacturer to manufacturer. You actually can service these by blowing them out in the reverse direction with compressed air. So if you had a filter like this, you would actually blow air through the inside out to remove any material. And usually you get like 30 different uses that way, but again, it depends from manufacturer to manufacturer. And the third type that we talk about are foam filters. It's a polyurethane foam, and it's coated in a glycol material, which helps to capture dust. Those are usually going to be life limited, or if it becomes particularly chock full of debris and whatnot, that will be a single-use item. It's discarded and replaced with a new one. The benefit being is that the foam elements are actually relatively cheap as opposed to the entire filter. So it's kind of an investment for the system, but then you're paying relatively low amounts of money to replace it each time. Now, as we talk about intake systems, you have to think about what we're approaching when we're trying to draw air into an engine. We really have two basic types. We're going to have a normally or naturally aspirated engine, and then we have turbo supercharged engines. So anything basically that's boosted versus anything that's not. And that requirement for airflow is going to change how we design the intake system. We can also look at things like what style of fuel metering we're using. If we're using carburation, then it's going to be susceptible to carburetor ice. On the other hand, if it is fuel injected, then we are not going to be susceptible to any carburetor ice because, well, there's no venturi with fuel being injected into the carburetor, but we are still susceptible to other kinds. So it's just important to remember what we're trying to accomplish and what kind of system it is to understand what we're looking at. So this in front of you is a pretty basic intake manifold system. We have the area where the throttle body would be over here, so airflow is going to come in through the inlet, in through the filter, and is going to enter our intake manifold over here. Now, what you see around here are those dreaded intake hoses. These are what seal our sections of induction pipe together. And an important part to notice about this is you see these little beads that are depicted on the edges. Those are where our hose clamps are going to bite, and the positioning of the hose clamp relative to that bead is very important, because if it's not exactly in the right spot, it's going to cause issues. Now, this is not the most efficient form of induction system you're going to see. This would be typical on something like a Continental 0470, where we have a single point of entry. It's going to separate in two directions to service the banks of cylinders on either side. And we put this crossover tube up at the front. The reason being is it gives us a little bit of pressure equalization. If we didn't have that crossover tube, then if there was one side or one bank of cylinders that was breathing a little more effectively than the other, then we would actually end up pushing more fuel air mixture that direction as opposed to the other, and we would considerably change the performance. So basically it just gives us kind of pressure equalization between both sides, and that allows both banks of cylinders to be fed effectively and efficiently. Now, on the other hand, we have a more efficient system. We would consider this a balanced intake manifold. And the idea with this is as you can tell, instead of having a single point entry with two pathways to get to either bank, we actually have a single point that comes through our throttle body, and then right after the throttle body, it is going to head off to each cylinder. Effectively, what this does is it makes sure that each cylinder has a fair chance or an equal opportunity for fuel air mixture to reach it, which ultimately will provide us more balanced flow. Now, this is going to change a little bit based on volumetric efficiency of each cylinder. And effectively, the more air a cylinder can draw because of good volumetric efficiency means it's going to get a little more fuel air mixture, as opposed to one that is struggling a little bit with volumetric efficiency. And that's where things like our compression test can come in handy, because if we have a leak through the rings, then not only will we see lower performance due to lower compression, but we're also going to see lower performance due to a reduced amount of fuel air mixture that's being pulled into the cylinders. That can be kind of a challenge that we have to overcome. Something else that's important to know is when we look at any intake system, if it's unboosted, naturally aspirated, really our throttle body acts as a cutoff point. So we have our throttle plate. Now, in most cases, if we have a partial throttle operation, right, then we're going to have an area of high pressure on the inlet side of the throttle body, meaning coming from atmospheric pressure or ram air, and we're going to have an area of low pressure inside the intake manifold. Why is that? because the throttle body is going to act as a restrictor, which means we have more pressure pushing on the outside of the throttle body. We're limiting or metering the amount of air that can move into the intake manifold, and that air is, remember, being sucked in by the cylinders. So whenever those cylinders draw air in, it's going to create a little bit of a vacuum. Now, as we go all the way up to full throttle, that is the closest that the intake system is going to be to atmospheric pressure because that throttle body is wide open. But remember, the air is drawn into the engine ultimately by a vacuum being generated by the cylinders. So no matter what power setting we're at, even if it's full throttle, we're still going to have that area of high pressure outside, and we're going to have that area of lower pressure inside the intake manifold, even if it's just by a little bit. Now, another piece that we want to talk about with intake systems is when we're dealing with intake leaks. It's important to be able to find these. Like I mentioned, those rubber hoses can be tough. If we have failed gaskets going into cylinders, effectively what's going to happen is it's going to cause our mixture to be artificially leaned out. Because remember, our carburetor up here is scheduling an amount of fuel for the amount of air that's passing through or past that throttle valve. So if we open up a leak downstream, now we're adding extra air into the mixture for the same amount of fuel, which means we're going to have a leaned out mixture. So when's this going to be most noticeable? Typically at idle RPM. You're going to struggle to get the engine to go all the way down to its idle speed. If your idle speed should be 500 RPM, we'll say it may want to sit closer to 600 or 700. Or if it's a really severe intake leak, you may not even be able to get the engine to start at all, or it may sound like you have a missing cylinder while you're trying to get that started up because there's just way too much air coming in, and we're already dealing with leaner mixtures when we're trying to start the engine. But that's the easiest way to troubleshoot that, is set the engine to idle and see where you're at. If you're trying to figure out where the leak is coming from, a lot of times we can take some starting fluid or a little bit of brake clean and spray it in the vicinity of those joints where the intake tubes connect together, or around the cylinder heads where the intake attaches on. And if you spray just a little bit of that brake clean, and what we'll notice is that brake clean will get sucked in through the leak and it'll be consumed as fuel, which means you're going to get a change in the tone of the engine, or a change in RPM when you spray that over a leak. So it can be a quick way to find leaks in a system. Now, looking at this carburetor mock-up here, I just want to point out a couple features that you're going to see in most intake systems. Now, we have our filter up front. We're familiar with that. We have the way that that's going to attach to the carburetor or the fuel injector valve, whatever it is. But there's a couple things we haven't discussed yet. One of those is this drain line down here. The reason we have this drain line is what can happen over time is if we overprime an engine, or if we move the throttle plate back and forth and it squirts fuel through the accelerator pump, then unused fuel can start to pool in the bottom of the air box, or the bottom of the carburetor box. Now that would be really bad if in the event we have a backfire or something like that, we could ignite that and just completely blow the carburetor box off, and you have a very, very potentially dangerous situation. It can start fires that way. So what we install is this drain line. So basically if we have excess fuel that accumulates in that carburetor box, then it's going to be able to drain out through the drain line, and we can avoid that situation. Now this is kind of a generic mock-up. There's a few different ways that are approached when we look at alternate air. And realistically, alternate air is a term that's used for all kinds of systems in an aircraft. It isn't just alternate air for carb heat. It isn't just alternate air for filtered air. It's basically any alternative flow of air other than the primary inlet. Now, the way this works, this is depicting a heated carb air valve. So effectively, we have heated air that comes in through a spring-loaded door when we actuate a lever that blocks off our ram air intake. Now, this is one way of doing things. In other cases, it may not be a spring-loaded door. It could be a hole connected to scat tubing to a muffler shroud, like you saw in the video just a couple minutes ago. On the other hand, it may be a system where we have a air filter that is susceptible to being iced up, and we have a spring-loaded door that will open if the main air filter is clogged. They all do different jobs, but they're all, technically speaking, alternate air. We'll focus in a little bit more on the icing side of that in just a minute, though. The other component we have here, which is not on everything, is a carburetor air temperature. And basically that's just going to tell us what temperature the air entering the engine is. and it's going to give us some general idea of if the engine is going to be more susceptible to icing or not. And then, of course, we pass up through the carburetor. Now, as we talk about icing, we'll take a look at three primary types of icing that we tend to run into. The first up here is impact ice. Impact ice typically is going to affect either the intake just before the fuel metering device, or it's more likely going to affect the air filter itself. This comes from having moisture present in the air. So if you're flying through rain, flying through snow, that ice is going to start to accumulate on the air filter, and typically it'll accumulate at a rate similar to what you'd see on the wings or other surfaces on the aircraft. The only way to do anything about this, we do have those guards on air filters to try to cause an area for ice to accumulate first, but ultimately if the filter clogs, then all we can do is rely on alternate air, which is typically going to be automatically controlled by means of a spring-loaded door. The one that we see more often and is really concerning is throttle ice. Now, throttle ice is something that happens when we have cold, moist air flowing in through a system, and because we have a Venturi effect of air passing between the side of the throttle body and the throttle plate itself, we're going to get even colder temperatures, which can cause ice to start to accumulate on the throttle plate itself. Now, again, you're going to notice a loss of performance. This is really not something that we would distinguish from carburetor ice because this is all happening in the carburetor, but ultimately it's going to cause diminished performance because of diminished airflow, and it can get more and more severe to the point where it can actually jam the throttle in a single position, which we can only rectify using some kind of anti-icing method. The third kind we see is a little more tricky because we don't necessarily have to see moisture present in the air for this to become an issue, but it's evaporative ice. Ultimately, what happens is as fuel is injected into the airstream and collects or swirls with the air that's coming through the throttle body, we're going to see that fuel diminish the temperature. Ultimately, we want liquid fuel to be completely atomized or emulsified into the air, and as a result, we're going to see the temperatures drop even further. So typically speaking, we can see carburetor ice form on a relatively humid day in temperatures all the way up to 70 degrees because of the temperature drop that we see through this entire throttle body system. Now, one of the causes of this, like I said, is typically going to be relatively high humidity because the moisture is present in the air and we drop the temperature. But as a result, if you're flying in conditions where there are visible signs of moisture, be it rain, sleet, snow, whatever it is, then it is absolutely going to be at high risk for developing throttle ice or fuel evaporation ice. And the other key about this is these types of ice will form before you see it form on the aircraft. This is important for pilots to know. It's also important for maintenance people to understand, but it's going to happen before you see ice. So you may not notice that you're in icing conditions, but it can already be happening. How can we tell? Well, we're going to see diminished performance. If it's a fixed pitch propeller, we're going to see reduced RPM, which may not be easily noticeable, which is why typically running the carburetor heat on a descent or over a certain interval of time, I should say, when you are not on descent in just suspected icing conditions, those two will help to prevent carburetor ice, and it kind of works off the assumption that there will be carburetor ice. So it gets built right into a checklist for flight crews. On the other hand, if we have a constant speed propeller, then we're going to notice a manifold pressure drop. We may maintain the same RPM, which is what the propeller is supposed to do, but we'll see the manifold pressure start to drop as that throttle body gets blocked off more and more. It's going to have the exact same effect as if we started closing the throttle body because now we're restricting airflow through. When we go to remove ice on these systems, we have two primary ways of doing it. If we're going to remove ice from the inside, we can either do it through an alcohol spray, so we can use de-icing alcohol, which is just going to get injected, usually at some point in the intake system. It's going to spray right down onto the throttle body and help to melt away ice with the alcohol. The other more common that we see is going to be using some kind of carburetor heat. Most commonly, you'll see that carburetor heat provided by a shroud around the exhaust, usually around the muffler, and that is going to move hot air into the stream. Now, just a thing to note about this is it's actually regulated the way that we build these carburetor heat systems, but they have to provide at least a 90-degree Fahrenheit rise at 75% throttle. So you can imagine the issue would be if we can't provide enough heat at cruise power, and we don't have the ability to get up to a higher power setting because of the effect of the ice, then we won't be able to clear away the ice. So ultimately, we have to get a 90-degree Fahrenheit rise at 75% throttle. The other piece about this is it's designed to be used for short periods of time, and carburetor heat systems are almost always going to be unfiltered air. So this gives us two warnings. The aircraft should not be operated on the ground for excessive periods of time, really as little as we possibly can, with the carburetor heat on. Because it's unfiltered air, we're going to have a higher chance of pulling in any kind of debris that's on the ground, and we can cause issues. Number one, when we talk about unfiltered air, is we can cause increased wear on the engine. You'll see the engine oil become dirtier much more quickly, and will reduce its lubricating properties. The other thing that's a little less noticeable, at least initially, is we can actually start causing silicon fouling of our spark plugs because of the dust and sand and grit that's being taken into the intake system. But that being said, carburetor heat is going to be unfiltered air, and so we want to make sure that we don't operate it too much on the ground. Also in flight, because carburetor heat is going to significantly heat the charge that we have moving through this system, we want to make sure that we use it only long enough to melt the ice. If we use it too long, then it's effectively going to change our mixture. We can lead to situations like detonation, knocking, all kinds of problems we don't want to have. So only use it long enough to melt the ice and avoid using it on the ground.